In this lecture, we will discuss about the hyperbolic functions. To define these functions, we will begin with the familiar formulae for trigonometric functions, namely sin z, which was defined as in the previous lecture, which was defined as e to the power iz minus e to the power minus iz divided by 2i, and cos z was defined as e raised to iz plus e raised to minus iz divided by 2. Now here we will replace z by a purely complex number iy. So that is, the real part of this number is 0. If we replace this z by I times y, this sin z simply becomes sin iy equal to e raised to I into iy. Similarly, here we replace z by iy divided by 2i, which gives us e raised to minus y, since I into I is I squared, which is minus 1, minus e raised to plus y upon 2i. Now we can adjust I in the numerator and the denominator. So this I into I gives us I squared, which gives us a minus 1. Now that minus sign can be adjusted here to get a plus sign for this term and a minus sign for this term. So we get e raised to y minus e raised to minus y divided by 2 into I. So this is sine of I times y. Similarly, we can see what happens with cos z. So cos of iy, this is a much simpler case. So we will directly substitute iy instead of z, and again following the same rule, this gives us e raised to y plus e raised to minus y divided by 2. Fine. Now we have come across two new functions which are put in the squared brackets. Now let us define these two functions by labeling them as hyperbolic sine and hyperbolic cos. So hyperbolic sine is written as sine h and hyperbolic cos is written as cos h. So we are going to take only the real part of this expression. So sine h of y is written as e raised to y minus e raised to minus y by 2, and cos h of y is written as e raised to y plus e raised to minus y by 2. So this is how we define hyperbolic functions. So we will also get a relation between the trigonometric functions and hyperbolic functions. If we substitute these two in the earlier expressions, what we get is cos of iy is just cos of hyperbolic y, and sine of iy is sine hyperbolic y times I. Fine. Now, since these derivations are general, This y could be any number. So let us say instead of y, we have to write these hyperbolic functions for complex numbers. So we will repeat these two formulae to write sine h of z equals e raised to z minus e raised to minus z divided by 2, and cos hyperbolic z equal to e raised to z plus e raised to minus z whole divided by 2. Yes. So we are going to regularly use these two formulae while solving the problems related to hyperbolic functions. Of course, along with these two, we have to remember the previous formulae, namely the Euler's formula and the expressions for trigonometric functions involving complex numbers, which we are already discussed in the previous lectures. As an example, we will try to prove that derivative of cos hyperbolic z with respect to z is nothing but sine hyperbolic z. Now note that this formula is slightly different, because in case of trigonometric functions we know that derivative of cos z is minus sine z. Now this minus sign doesn't appear here. So let us try to prove this. So we can start with d by dz of cos hyperbolic z, which equals d by dz of, now let us use this formula of cos hyperbolic z as e raised to z plus e raised to minus z by 2. This 1/2 can be taken outside the derivative since it's a constant. Now the derivative of e raised to z is just e raised to z plus derivative of e raised to minus z is e raised to minus z into minus 1. Now this is nothing but e raised to z minus e raised to minus z by 2, which is defined earlier as sine hyperbolic z. So yes, derivative of cos hyperbolic z is sine hyperbolic z. As a part of exercise, we can try finding out what is the derivative of sine hyperbolic z. So this can be taken as an exercise. We can also try, so let us clear the canvas. Now we will try to simplify some expressions or to find out the values of some expressions. Let us begin with an example, with an example which says to find out the value of cos ix in terms of hyperbolic functions, So yes, for this we are going to use the previously derived formula for trigonometric functions. Cos z is e raised to iz, right, plus e raised to minus iz whole divided by 2. So here z is to be replaced by I times x. So we have cos of ix is equal to e raised to I times ix plus e raised to minus I times ix divided by 2, which gives us e raised to minus x plus e raised to x divided by 2. Now this is clearly the cos hyperbolic function of x. Good. So we are able to express a trigonometric a trigonometric function cos ix in terms of an hyperbolic function cos x. Let us try another example which says us to find out the value of cos hyperbolic of 2 pi I. Now let us follow through the steps by using the definition of hyperbolic cos z as e raised to z plus e raised to minus z divided by 2. Fine. So here the z is this 2 pi I. So we will do this as e raised to 2 pi I plus e raised to minus 2 pi I divided by 2. Now in order to further simplify this, we must know the Euler's formula, that e raised to e raised to plus or minus I theta is cos theta plus or minus I sine theta. Now compare this expression with the term present here. This theta is this 2 pi here. So for this first term, I will write cos of 2 pi plus I sine of 2 pi plus for the second term, I will write cos of 2 pi minus I sine of 2 pi. Since we have a negative sign here, we will have a negative sign here as well and divided by 2. So clearly these two terms will cancel out with each other and we will have 2 times cos of 2 pi, that is the addition of these two same terms, divided by 2, which is nothing but cos of 2 pi. Now what is the value of cos of 2 pi? We know that cos of n pi is minus 1 raised to n. So this is just minus 1 raised to 2, which is plus 1. So the value of cos hyperbolic 2 pi I comes out to be equal to 1. Let us try another problem which is slightly complicated than this. To determine the value of tan hyperbolic of 1 minus I pi. Now this is a two-step process, obviously, because tan could be written as the ratio of sine hyperbolic of 1 minus I pi divided by cos hyperbolic of 1 minus I pi. In the next step, we should determine an expression for sine hyperbolic of this and then an expression for cos hyperbolic of this. So let us start with the sine part. So sine hyperbolic of 1 minus I pi. If we remember the formula which says sine hyperbolic z is e raised to z minus e raised to minus z divided by 2 and cos hyperbolic z is e raised to z plus e raised to minus z divided by 2. So here we have e raised to 1 minus I pi minus e raised to minus of 1 minus I pi divided by 2. Now note that e raised to a plus b can be splitted as e raised to a into e raised to b. Good. So we will write it as e raised to 1 into e raised to minus I pi minus e raised to minus 1 into e raised to plus I pi. Since this minus becomes a plus divided by 2. Now this e raised to plus or minus I pi just gives us cos pi plus or minus I sine pi. Why I am including both the signs, plus and minus? Because at one place we have a minus I pi and at the other place we have a plus I pi. So this is nothing but, now note that this cos pi is just minus 1 and sine pi is 0. So in both these cases e raised to plus or minus I pi is just minus 1. So let us use this here. And write e raised to minus 1 into minus 1 minus e raised to, e raised to minus 1, just a minute, sorry, there is a correction. So this is e raised to plus 1 into minus 1 minus e raised to minus 1 into minus 1 divided by 2. So this minus 1 can be taken common and here we get e minus 1 upon e. So this e raised to minus 1 is just 1 upon e and e raised to 1 is e. So this is the value for sine hyperbolic of the 1 minus I pi term. Now similarly we can try with the other expression, which is cos hyperbolic of 1 minus I pi, which will be by using this formula, which is cos hyperbolic of z equal to e raised to z plus e raised to minus z by 2. So here we have e raised to 1 minus I pi plus e raised to minus 1 minus I pi divided by 2. By following the similar discussion which was done for sine hyperbolic of this number, we will get here e raised to 1 into minus 1 plus e raised to minus 1 into minus 1 divided by 2. That is minus 1 by 2 into e plus 1 upon e. E plus 1 upon e. So there is just a difference of the plus and minus sign. Now we can have this tan hyperbolic of 1 minus I pi as e minus 1 upon e into minus half, which is the expression for sine hyperbolic, divided by e plus 1 upon e into minus half, which is the expression for cos hyperbolic of 1 minus I pi. So this is just e squared minus 1 upon e divided by e squared plus 1 upon e, since these terms get cancelled. So tan of 1 minus I pi is going to be e squared minus 1 upon e squared plus 1. So this is how it is to be done. So we can keep on trying such problems which we can find in any standard book which involves discussion on complex numbers and functions involving complex numbers. Thank you.